Perfect. All right. Hello, everyone. Welcome back to our last career talk of the AI Research School 2023. Today, we have the pleasure to have our speaker, Matthew Abueg. And I will do a brief introduction of Matthew. Matthew has been working at Google Seattle for 6 years, applying machine learning to research and products such as maps, COVID modeling, and Google Health studies. His research covers areas including privacy, fairness, and sustainability using on-device learning, recommendation systems, reinforcement learning, and information retrieval. He's always looking for ways to encourage improvements to urban planning and to make cycling accessible and ubiquitous. And today he is going to talk to us about industry research, specifically in reinforcement learning. Thank you very much, Matthew, for giving the talk today. Please go ahead. Thank you.
Yeah, thanks for having me, and thanks for the intro. So yeah, this will be my talk. I'm gonna go ahead and move the Zoom. So if I'm looking awkwardly off to the side, that's where you guys are, so I can see if people mention things in chat, just to have you off to the side here. But so yeah, so I'm gonna be talking a little bit about industry research, a little bit about reinforcement learning, but feel free to stop me with questions or whatnot. This is mostly for your time, for me to answer things that other questions you may have that you maybe didn't get a chance to ask of my two colleagues or whatnot. But a decent amount of my recent work has been in reinforcement learning, so that's why I thought it would be a reasonable overarching thing to talk about today. So what are we going to talk about? In particular, I will talk about what is reinforcement learning, since I don't know if you guys have necessarily covered that in your workshop. And then some examples of its uses. I'll kind of run through some again. Feel free to stop me if you're curious more about some of them. Some I can speak more to, some not. And then kind of throughout, I'm also going to be kind of maintaining some of the themes of the things I think about when doing industry research. And then one particular application to things that we're working on kind of right now, or in the recent past at least. And I have a spot for questions. Feel free to stop me there or earlier. And then there are a number of other areas, as was mentioned, that I have worked in / have interest in. So if we have extra time and it doesn't get filled up with your questions, I'll probably jump to some other fun areas. Okay. So I just wanted to throw this up kind of as a little thought that I'll kind of be guiding as we go along. There are a lot of things that we care about for kind of general ML and AI when we're doing research. Some of them apply to both industry and academia. Some of them are a little bit more specific to some of the concerns we have to face in industry. These are kind of just some things we tend to be thinking about a lot. There are whole teams devoted to any one of these areas, but as an individual ML researcher, you probably have to think at least about all of these a little bit, and sometimes a lot. So everything, obviously accuracy is the first thing in here. I'm kind of abusing the term accuracy to talk about just how good is your model. So, that's obviously very important, but then there are all the other areas. Particularly, we care a lot about privacy, and in my work is a lot devoted specifically to privacy. So ensuring we don't leak users' data, ensuring that we have minimize access internally and externally to data, move data around as little as possible, and things like that. And along with that goes the security of the data too. And then there's a lot of scaling considerations, as you might imagine at Google. We try to do most things at what we call Google scale, which is, not just serving a few people in most cases, usually serving millions or billions if we can. So there are always questions about how to scale up models and the trade-offs you have in terms of speed and accuracy and things like that. And then interpretability is a very interesting one, especially you'll hear more and more in recent times, with things like these huge models. What can we do to try to understand how they work, why they work, and such? Reliability, We want them to work well. We also want them to work well over time under edge cases, under skew that might happen as you bring things to production. Fairness is another one that I care a lot about, trying to make sure that as you slice the model's performance, you don't just care about one accuracy number, you do care about accuracy across groups or across what might otherwise be termed edge cases, if it works better or worse for certain populations, especially systematically underserved groups. And abuse is one we have to care a lot about. All these things, someone's going to try to use them adversarially to do bad things with them. And we want to think about how that might happen, how we might minimize it, build in ways to counter it, to detect it, and such. So with all of that said, let's jump into actual reinforcement learning. So what is reinforcement learning? Basically, you have this little loop here where you have an environment, you know, something is going on in the world. You have an agent at the bottom there. And then you have this loop where an agent is going to take an action in the environment. They might move around or something. And then someone will tell them whether that movement was good or bad. And they'll use that to update their knowledge about the world and about the actions they make for the future actions to hopefully move around better to reach whatever goal this reward is trying to get them to do. So one little fun example that you often see in AI textbooks, for instance, is the cart pole example, where you have this little black box, the cart, and a pole sitting on top of it. And the pole will fall if you don't do anything. So you have to move the cart left and right to keep the pole up. So in this particular case, you might want to, you want to think about what the cart has to do to keep this pole up. So in particular, right, as the pole is starting to fall, you want to move the cart in that direction to try to keep it up. So that's what the agent is in this case. It's this cart. And then what the reward function is if you're keeping this pole up. So you get rewarded for keeping the pole up. If it falls, you lose, you get a bad score, basically. So you can imagine creating a model. The agent, we usually have some sort of model for this agent. You can take it as simply as a decision tree, which presumably you've talked about a little bit, or other simple models like this. So for instance, you could say, if the pole is leaning to the left, I want to move left. If the pole is leaning to the right, I want to move right. That'd be a very simple model that you could have. Obviously, it's not going to cover all the real cases, you know, with speed and momentum and angles and things like that. And you could obviously make this problem more complicated if you added wind or gravity, basically, that could actually operate not, you know, in a linear fashion. And then you can even get more advanced. This is another fun example of reinforcement learning. You have this little person-like thing that's trying to run. In particular, the reward function is you get rewarded for moving forward. And that's all that they are told, basically. Anytime this person moves forward in this space, they get a positive reward. So you have to figure out everything like moving the legs, hinging the body to avoid obstacles and whatnot, such that you are able to keep moving forward. And you know, if it were to hit one of these red things, it would stop moving forward, it would stop moving at all, and it would stop getting rewarded or get a negative feedback. So let's get into some actual uses of RL besides just fun little toy examples. The one that, if you guys have heard of RL before, that you've probably heard of is self-driving cars. It's one of the classic examples. Is robotics is where it's used quite heavily for, self-driving cars as being one of them. So for instance, you could say that the reward, for instance, you could just say, don't crash, right? That's a reward that could work, but it would be pretty challenging to have learn a whole RL system just based on don't crash, right? There's a lot more that a car wants to do besides not crash. So you could try to think about what is a better reward than that. Maybe, again, you could have something like moving forward or reaching your destination. And you'd want to think about how to craft that reward to make your problem as learnable as possible. And in particular, there's this notion of a proximal reward, where you want ideally to be able to have information as frequently as possible. So, every time I make an action, ideally I want to get some notion of reward. It doesn't always happen. Sometimes you have to make multiple steps before you get that reward. Another robotics example being like robotic manipulation, like if you have a hand, a robotic kind of hand, trying to pick up objects and put them in a box. So trying to teach it to do that ideally on its own. Jumping back to the games a little bit, you may have heard of AlphaGo or AlphaGo Zero, which was DeepMind's attempt to learn to play games. There are two ways that it did this. One was by imitating a pro. So we call this actually imitation learning, where a professional player makes moves and it watches as this person makes moves. And it learns to try to replicate that behavior, to try to move the way they did. It did very well. It beat a number of pros, and then they decided to try to see if they could do it without having to have any expert examples. So AlphaGo Zero was just learning by playing a lot, basically. And in fact, some of the tricks there was it learned basically to play against itself and update its policy in a way that it wouldn't have to play as much as it used to in the past. This seems like a simple enough principle that they might have just tried it first, but it's actually quite challenging because, again, in a game as complicated as Go, you wouldn't want the only reward to be that you won the game, right? That would be a very long proximal reward. Like it would be very hard to try to learn every move that leads to a winning game versus a losing game. So in particular, they had some strategies for how to do this. They had an intelligent neural network that could sort of predict the outcome of a game given a current state. And they kind of paired the learning of that algorithm that predicted the outcome from a state with the algorithm for actually learning how to play the game. And this actually helped them to learn much faster, because otherwise you have to do this kind of state space exploration where you'd say from any given state, let's try to play out and see who the most likely person is to win. So they would have these little rounds, they're called the rollout of the policy, where you try to see from any state who is likely to win, and that's how you would give your reward. But that's obviously very slow. So that was a nice development they managed to have there. And a similar kind of idea that I thought that I would love to try and is actually getting tried more and more now that these AIs are getting more advanced is, for instance, AI opponents for game development. I know one challenge in the gaming industry is that it's really hard to play test your games, right? Especially these like MMO kind of game, multiplayer games. It's very hard to play test them. Most AIs that are built for them are pretty terrible, so it's hard to tell if the game is actually designed well. But if you could be using reinforcement learning to kind of learn how to play games quickly, especially as games evolve and change and have new features added, and quickly having AIs learn how to play them would be great for game devs. And to get as current as possible, one of the biggest uses for RL in recent news is with large language models. Was one of the key developments that enabled ChatGPT, for instance, and our own system, I believe, as far as I know, but don't quote me on that, to do so well is a reinforcement learning component. In particular, it's learning to judge how good a summary is. So you can take a generative model, like most LLMs, have them output text, but how do you know if this summary is actually good? Like it could be accurate. You could like look for what words are in it and see if it matches the words that are in an expert summary. That's the, whatever. Yeah, you can still see me, I think, right? Yeah, okay. It likes to think it likes to turn off the lights. Okay, so where was I? Oh yeah, so you could try to just look for like word overlap, for instance, with an expert summary. This is the old way that most summarization systems were evaluated, and I really hated that as an evaluation methodology, because then you could just have some weird bag of words that just contains all the relevant words, and that would be a great looking summary, even though it wasn't natural. So this new system of basically learning how humans prefer summaries, and in particular using this sort of which summary do you prefer most between two of them, was a very strong advancement that has helped these algorithms, these generative models, produce much more natural summaries. And the one other small note there is when doing these sorts of human feedback, humans are much better at ranking items than they are at just giving an arbitrary number to associate how good something is. So like if we're given a summary and said, score this summary 1 to 5, you'll get really inconsistent results from how good humans say a summary is on a score of 1 to 5. But if you say which summary of these two is better, humans are way better at doing that. Just a side note, if you're ever trying to get human feedback on to try to train things, pairwise rankings are much better. So jumping back. So this reward predictor was actually built into the whole algorithmic framework, where the system would try to generate a summary, and then it would get told, is this summary better or worse than the summary I would have generated, for instance, in an earlier iteration of my model? And if it's better, then we're going to keep the new parameters. Otherwise, maybe we'll go back in time to the older parameters. Here was the fun little visualization of this. For instance, if you, in more of the gaming space that was used to say which one of these gameplays was better. This was just asking humans for this feedback. So for instance, at a quick glance, you can probably tell that this one on the left might be doing okay, but it's just jumping back and forth, versus this one on the right that's losing because it hits the blue one, but is making more progress. So it's an interesting question of establishing who's better or worse, or which model is better or worse. Another very interesting application that was done lately is a field called meta learning. Basically, there are lots of different hyperparameters that are used. I assume you guys have talked at least some amount about hyperparameters in your ML models. But as models get more and more complex, there are more and more hyperparameters. It's not just like learning rate. Or even model complexity. How deep is your model? How many parameters does it have in these things? These are all potentially tunable. So they actually used RL to try to find the best model architecture from a relatively infinite size potential space of model architectures. So in particular, you can see here that they did a random search to start, and then they did an exploration with a refinement step, and then they did one with full RL, and it found much better models, and it found the models faster, and it actually created this nice trade-off, as I was talking before, about the latency versus the model quality. And this is another thing that I was saying we care about is, sometimes you can trade model quality for latency sometimes if you really care about that in your scenario. So that's RL, and there's this whole opposite field called IRL, or inverse reinforcement learning, which you want to actually learn that reward function or the policy itself given examples. And that imitation learning that I mentioned before is actually an example of that. Sorry, did I see a question there? The entropy and maybe I'm sorry if I'm not understanding this question entirely. Let me pull it up here. Oh, okay. Maybe it looks like it's getting answered already. Oh, no. Entropy and the element which are largely entropy. So there are, if I'm understanding your question correctly, is this that how what are the best ways to evaluate or train models, especially large language models? In which case, basically, there are certainly lots of different measures for large language models. Perplexity is one that's very commonly used, especially when you're evaluating it across domains. Yes, it is certainly not just entropy, but for any reward function, you can define any reward function you want for RL, right? That when I say better, it can be better by whatever metric. This is when it's human feedback, we're talking about just human preference and not any particular actual evaluation metric. Feel free to clarify if there's more you wanted there. So imagine that we're watching this pole cart and we're trying to figure out why it's moving the way it does, right? So we can see that the cart seems to be trying to hold the pole vertical. So we can establish that this is the reward function that it was going for. Maybe it's wrong, maybe it's not. And similarly with this, right, we could just see this weird little thing running through space and wondering why it's doing that, noticing that it's avoiding obstacles. We could say that the reward function might be to avoid obstacles or might be to keep the legs moving, but we might be able to understand that it is actually just trying to move forward. So this is generally when you have demonstrations and you want to try to learn from those demonstrations. So this is the other half of what's done in self-driving cars. So for instance, you have imitations of people driving and you want to learn how to, for instance, avoid other cars in the road, learn how to stop and things like that. And especially you want to create this reward function or policy, depending on your circumstance, about how to do so, just based on expert demonstrations. And one interesting note here with the self-driving cars is that when they had examples, they only really started out with examples that were positives, right? You aren't in general going to ask some human to get into an accident in order to learn what an accident looks like and get a negative reward and then learn to try to avoid that. So what they would actually do is they would have synthetic perturbations where they would say, if we had turned the wheel to the right here instead of to the left like they did, it would have probably caused an accident, and use that as an example of an accident. Of course, they do have some examples probably of accidents too, if they happen to happen from the self-driving car in the real world, but they're fortunately fairly rare. So now we're going to get into an example that of the work that I've been doing, and I wanted to throw this up just because we're going to be thinking about these some too in this example. So as I was saying, I like cycling, and I want our directions to be as good as possible. So one example here in this IRL scenario is which of these paths is best, right? There are 3 paths here. Maybe everyone would agree that one of these paths is best, maybe not. So we want to understand why the user takes the path that they take, right? So we may know that the user did take one of these paths, but we don't necessarily know why. So we're trying to learn what their reward function is, what made them choose the path they did. We could talk about what makes a path best from a lot of different perspectives. We could talk about it overall, like on average. If we had to only suggest one path, which path would we suggest? We could talk about from a personalization standpoint. We could say, if I know you and know the paths that you've taken, which path would I suggest for you? And that might be different from other people. And we could talk about this kind of in between in a kind of what we call diversity perspective, where we say, if I have the capability to show 3 paths, which 3 paths should I show to kind of cover the greatest number of people or the greatest number of uses or variety of some sort. And you can define lots of different diversity metrics too, which can be interesting in itself. So learning the best possible path from A to B for all A to B pairs is intractable, right? Like we're not going to learn every best possible path from A to B, like the entire path for all possible origins and destinations in the world. So we want to learn characteristics of the path, or in particular characteristics of subcomponents of the path. Like for instance, each street that you drive on, each segment of it. And we want to learn what makes an individual segment better or worse, or the transition from one segment to another, like stop signs or the lack thereof, or the bike lanes, and such things about streets, and how much people care about these different features. Maybe in general, people really like bike lanes unless there's a stop sign, for instance. So we want to learn kind of how that model would look. So we're trying to learn this reward. So as I said, our goal is to find kind of the optimal path from A to B, where we define optimal as the path the user took, right? Maybe that's wrong. Maybe that user was just bored that day and decided to go on a roundabout path. Maybe that gets handled in the aggregate. Maybe it doesn't. Maybe we have to define what a user is. Right? We get into some pretty nitty-gritty things here about the specifics of our data, as is one challenge always, is kind of how to clean up the data before we even start using it, or how to analyze what we would want to learn from. And then we also want to understand if our current policy is taking a specific path, we want to know, is that path better or worse than that user's path, and by how much? Because in general, when you're when you want to update your policy, you need to know how much to update your policy. So you need some sort of notion of a difference between the path that we chose and the path the user chose. And then we average that across all of the examples we have, and then we can get some sort of metric about how good our model is right now. And then we finally want to minimize that. So what kind of data do we have? As I said, is kind of one of the other major questions, right? So we have the path the user took. We have some notion of what all the other possible paths are. Ideally, again, we wouldn't want to have to enumerate every other possible path, because that would be a huge number. But we want to learn about at least the possible segments or maneuvers along that path, such that we could construct any arbitrary alternate path. And then information about the roads themselves, whatever our input features are going to be. Things like, does it have a bike lane? Does it have a stop sign? What is the speed of the road? And things like any other thing you can imagine. So as you might imagine, there are a lot of potential issues here, as I wanted to come back to in our particular circumstance, right? So privacy, we want to make sure that we're not like learning one exact user's route. Right? We don't want to make it easy to just find like where one person goes every day because they're the only person that happens to bike in this area. We want this to scale, right? We want to be able to compute these paths relatively quickly when someone asks, again, like in maps, if they were to ask for a bike route, we want to be able to quickly give our answer. If it's this huge model that would take a long time to give us what the good route is, or if it would take too long to learn, maybe we won't have enough time to be updating it as frequently as we might want to for changes in road conditions. Ideally, we want it to be interpretable. This is always a tension, especially when you're adding ML to a product that didn't have it before. For instance, there's this tension about interpretability of your model. So for instance, how people want to know how people want to be able to understand why it's making the decisions that it does. And you can choose your model complexity to be able to understand it better. You can also do a number of other strategies. Maybe you'll talk about it during your this whole workshop, but if not, that's a whole nother very interesting field about interpretability, like black box interpretations and things like that. Reliability, right? Like there are a lot of random roads that may not even be covered in your initial data set. You want to know that it's not going to break in some circumstances. You may always want to get someone to up to the destination, even if it's not optimal. So you don't want it to break down and not be able to find a path, for instance. And then fairness, you we think a lot about where we're deploying this and the kind of differences, like road conditions can be very different in different countries. There can be a lot of other issues from one region to another that could, if we, for instance, I only trained on US data and then I tried to apply this in another country, maybe a country that has more two-wheelers, for instance, to contest with bike routes, or maybe doesn't have bike lanes, or, well, a lot of places in the US don't have bike lanes too, but we want to be sure that we can evaluate our model in a lot of different regions to understand how well it does. Maybe even we'll build separate models for different regions. And then finally, abuse. There's a lot of considerations for abuse in geomaps. You may have heard of some in the news. Some of them are amusing, some of them I'm sure are very frustrating for the engineers that designed them. Things like you wouldn't want someone to be able to do some really bad trajectory 1,000 times that you then learn from, and then it would screw up your whole routing system. Or you wouldn't want to try to say that this particular route is so busy so that I navigate everyone away from it, even though it is an optimal route, right? Because how heavy traffic is on a route might be another one of your features, for instance. So, oh, I thought I had one more slide. Well, I'll just come back to this one. But so basically, those are some of the considerations we have when we're trying to think about how to route. And in particular, we have this IRL framework that we're developing in order to do exactly that. To be able to say, given a set of user trajectories, how can we do this? And how can we do this at scale? Scale is one of the major issues of reinforcement learning algorithms, especially historically. It's very hard to do at scale. So we have a number of optimizations that we do, like that one that I mentioned before, for instance, about how you roll out the policy to be able to understand what's the best one. You can have approximations to that via neural networks or via varying horizons, basically how far out you'll look from your current point when you're trying to roll out the policy. So that is it for my discussion of reinforcement learning. I'm happy to take questions or go on to other things I find interesting.
Thank you very much, Matthew, for the talk. I think right now we're open up for questions. Got many clapping hands here. So we'll go with the first one that Farzan has asked, which I think you read before. So are the entropies the only way to mature a large language model? Can we put these models into different situations and by mirroring the difference output, find out more metrics about them? He meant perplexity, cross entropy, and bits per character. If you understand the question, please go ahead. If you need more explanations for them, you can feel free to unmute and elaborate further.
Yeah, I'll try to answer that a little more fully, but yeah, feel free to unmute and ask more too. But yeah, as I was saying before, there are lots of ways to measure the quality of a model, and can be very interesting to try to use a model in multiple scenarios and see how well it does. That's kind of one of the major things about LLMs that they've been doing, is trying to apply them to multiple scenarios and seeing how well they do, and by different metrics. Cross entropy is often used as the loss function, basically how you measure the model during training. You don't really use perplexity in general for training, but you do use it as one of your evaluation metrics, oftentimes for summarization.
Okay. Thank you. And first time, if you have no further follow-up to that, I'll start asking the next question from Umar. When given a problem like this, are you the one who decides what features to use and what data to collect, or are you given the problem and data set and asked to make a model? So it's more like a job description kind of thing.
Yeah, no, that's great. That's a good question. Well, yeah. I think you guys can still see me even though my light turned off again. It can depend a lot. In general, when you're, I don't know, yeah, it can depend a lot, especially at what stage of the research your project is. If it's in the earlier stages, oftentimes you actually have more of the freedom to kind of explore these things. As a project gets more towards like maturity or graduating into a project or like a real product, you often actually end up being a little more constrained based on what exists, what data is collectible or things like that. Our app, Maps app exists and collects sort of what it collects. We can ask for some new things to be collected. One of our team's objectives and actual successes was getting a pretty interesting new feature collected. And that was something we pushed for, but was a longer endeavor. But in general, I like to start as broad as possible and then figure out where I'm constrained. So in particular, unless it's really coming more from the product team. So in one of the maps cases, especially for that interpretability question, one place we wanted to start was how much better can we do with our IRL model than their current system. So we basically took the exact set of features they were using and tried to run our system on it. So then we were constrained by the features we were using. The data we could manipulate a decent amount because we could say, how do we want to clean it, which portions of the data we want to use, especially when we were talking about like different locations and things like that. Yes, I'd say that's true.
Thank you. And I guess in following up on the interpretability side of things, Sebastian asked a question on do you need experts in interpretability, scaling, fairness in each team, or do you have to learn about every single subfield?
Yeah,
as your position.
That's a great question. It helps for sure to have experts about all of these subfields. In general, on each team, you won't have experts in every one of these. You'll probably have experts in the things that are most salient to whatever you're working on. But it is definitely one advantage of being in a large corporation, as is often true in a large research department. You'll have other people that you can talk to, even if they're outside of your team. You can consult with on particular problems that you might have. So I can go ask, like, if there was something that I wasn't an expert in fairness, for instance, I could ask the responsible AI team about some of their thoughts on something. And then there are definitely a lot of people that help with scaling issues. There are two people that are much better suited than me to a lot of scaling questions, especially when you actually want to try to put it into the product, understanding the nitty gritty about the scaling issues that come with that product too.
Yeah. And I guess from your experience, because you're working in an industry, if you've worked in an academic setting before, sort of what do you see as the differences or the similar challenges that you encounter, and what do you obviously I think that in terms of the scaling issues, it sounds at least to my feelings, it's easier to scale very largely in industry, which is sometimes that's a luxury that we don't quite have in academic settings. Or what do you see as the I guess the advantage and disadvantage from both sides?
Yeah, that's a great point. We definitely, so yeah, when I was doing my PhD, I definitely did much smaller level things. I would say it is a bit of a double-edged sword in industry. We have a lot of the resources to scale, but as a result, we are expected for a lot of things to be able to scale. So
Okay.
if you built an algorithm that couldn't scale, no one will pay attention to you. So it is a bit of a trade-off, but no, it is certainly, I feel very privileged to be able to, for instance, if my algorithm worked well on a single metro, for instance, rather than necessarily figuring out how to scale it to the world, I could just run it 1,000 times across like 1,000 different jobs, right? And then
Right. I just one last question before Farhad, sorry. If you so on this topic, then how would you feel like it's the, I guess, the priority of importance when you're building an algorithm in industry? Let's say, would you put scaling before other things? What would you put first, second, and third?
Yeah, it's a great question. I think it depends a lot on the project. I can try to think of a couple examples at least to kind of motivate my thoughts. I think, well, yeah. One way you get around scaling or latency and all those things is if you can make your model not in kind of the critical path to like serving. So like if you can um, generate your inferences offline, for instance, basically can you like run it over all the data and then save the output of your model? That then you get to stop caring about scaling, for instance, and you can care a lot more about the other things that you might care about more. That's one way that we try to avoid it a lot of the time. And a lot of use cases are like that, in which case, so you get to kind of ignore scaling to some extent. In which case, it kind of depends a lot on, for instance, how sensitive you declare your data, or you think about your data, or your privacy groups or whoever you're working with thinks about your data. Right. So for instance, if we're talking about like publicly accessible information on the web, some people may think about that as less sensitive versus like, your phone's tracking of where you are, that might be very sensitive. And so the privacy aspect of your model might be paramount. So for instance, one thing I care a lot about is the privacy aspect of things. So seeing how much we can incorporate things like differential privacy, which try to limit the contribution of any individual to a model, so that you couldn't basically uncover any particular user's information, or federated learning, where you wouldn't even have to centralize the data. You can keep the data on every individual person's phone and just trying to learn model updates. Yeah, so our team particularly cares a lot about privacy, so that's where we do a lot of our focus.
Right, thank you very much. Sorry, please go ahead, Farhad.
Yeah, first of all, thank you for the presentation. That was a great talk. For some of our audience, perhaps this is the first time they actually encounter reinforcement learning in this school, AI school. So what's your suggestion for those who want to start the journey in reinforcement learning? Any specific suggestion, guideline, resources that you want to put out?
Oh, that's a good question. Yeah, I'd have to. There are, depending on how deeply you want to start diving in, there's a great book on reinforcement learning that you can just start with. Otherwise, I mean, my first AI class happened to be taught by someone who cared a decent amount about reinforcement learning back in undergrad. So we, for instance, did code up like the cart pole example as a pretty simple starting methodology. You can, if you want to kind of just start getting your hands dirty, that sort of is one way to do it. There are a lot of other examples like the cart pole one that you can find online that can kind of teach you a lot of the kind of specifics of reinforcement learning. One thing that I don't actually like about reinforcement learning is how particular they are about some of the terminology in reinforcement learning. So you'll notice I use the terms imitation learning and policy and reward. Some of those terms all have like very specific meanings that can be challenging to understand. So it can help to kind of like get your hand a little dirty, at least with like figuring out what is the difference between a policy and a reward, and when you care about imitation learning versus Q learning versus standard IRL. And yeah, but whether you learn best from book, there are a couple good books on reinforcement learning. I'm happy to send it after this, or if you just want to, there are tutorials on the web where you can do things like that.
Thank you very much. Oh wow, we have a few more follow-up questions from here, from Farzan again. If we can change some, if we can somehow change the way of answering these large language models are generated, and then extract a sample of fixed questions like trustful QA from by calculating the difference in the answer by something like the Shannon entropy equation, can we create new metric to measure large language models? I think this is a follow question to previous evaluation metrics question from Farzan.
Yeah, if I understand correctly, I think, so one thing that they have been trying to do, so there are a lot of ways to do things like this. One thing that they have been doing a lot, if you're familiar at all with large language models, you're probably familiar with the context component of the large language models, which is hugely important to their performance. In particular, this is basically the prompt that's fed in that tries to get the answer out in a summary in as clean and nice a format as possible. So there's a lot of information that goes into this prompt engineering, even from the research perspective as well. And in particular, there's the step beyond that, which is called prompt tuning, which is actually trying to learn a better prompt through some examples. And I think this gets a little closer to what you're trying to say here, where you have these sort of like fixed questions that you'd kind of ask of different types of models to try to figure out which one's best. And then you can, there are a lot of metrics for trying to evaluate which model is better. As I was discussing a little bit, entropy is, I love entropy for a lot of purposes, and it can be used here. You have to define your entropy kind of carefully in terms of, this is why I don't like things like BLEU, which try to do similarity just based on like word overlap. But if you can look at it in terms of like the probability of output of the tokens from the model, if you have the ability to peek into the model itself, then you can indeed start to analyze things like the entropy and perplexity of the models as well, and understand the difference. And that gets a bit towards these interpretability things that have been done to some extent, basically where you treat the model as a black box as much as possible, and you do these what's called like a facet analysis, where you change a very small portion of the input and see how it affects the output. You can even to some extent see how it affects the model weights themselves to try to understand how the model is working. In these billion parameter models, you probably wouldn't do that anymore, but that's when you can just look at the output itself and how the output changes with respect to changes in the input. And then you can kind of create these landscapes of understanding the model that way.
Thank you very much. I think we have another question from Andrew. This is related to working at Google. So at Google, is there a single collection of data to be used by all products? For example, maps versus web searches, or does each product collect different data for itself? This is many sub questions, so let's go with this first.
Sure, yeah. I can answer that as much as I know and I believe I can, but yeah, basically, we care a lot about the security and privacy of people's data. So actually getting access to data when it's not for the like, in general, access to data is limited to the people that are using the data to improve the product that it came from. And that's like kind of an overarching policy. So using things for other purposes is, you basically you have to go through like legal to make sure that it fits within privacy policies and acceptable use policies and things like that. Because a lot of the policies are crafted specifically for talking about that we will only collect people's data to use it to improve products. Yeah, I think that's the clearest way I can answer that question. There are a lot of privacy and security hurdles you go through if you want to join data, for instance.
Okay. And then the next question is also from Andrew. Can the decision from Google Maps, for example, the users in Calgary normally prefer Deerfoot Trail over Stony Trail, be used to improve search results for Calgarians? For example, give search results relating to Deerfoot Trail instead of Stony.
Yeah, I'm not on either of those teams, so I can't speak to that specific example. In theory, it's possible if the teams have agreed to craft their privacy policies to do something like that. I can't speak to that specific example. We've done some interesting research things that have been published. I don't know, like one one that I found interesting was like the Google flu trends, if you remember from forever ago, when they tried to utilize how people searched to try to understand how the spread of flu was happening across the world. And they actually got pretty accurate in that, but that was a little bit more of a researchy thing than an actual product application.
Thank you very much. And then we have another question from Sebastian. Sebastian, you can feel free to ask this yourself as well. So Sebastian is the program co-chair as well. Sorry, go ahead.
Hi, thank you very much for the presentation. That was very interesting. So my question is about more of a career question. How do you end up working as a researcher in industry? Because like from my point of view, there are very few positions in industry for research. So what's your experience and what would you recommend for someone who wants to do research in industry?
Yeah, it's a very good question. I think to some extent, I'd have to ask you how you personally define research. Because like what a lot of things that we do fall into more or less into research. If you mean like actually be a research scientist that's mostly focused on publishing papers, yes, that tends to be a bit of a rarer job and is harder to find. But if, for instance, you're more interested in like straddling the line a little bit between like making advancements on research and then applying them to products, or like the kinds of things that you'll see a lot of like NeurIPS that from Google and other large tech companies. Those positions are less rare and people enter them from all sorts of different avenues. So for instance, my job doesn't actually have the word researcher anywhere in it. I'm just technically a software engineer at Google. But it so happens that, my background is such that I have a strong research background, and I joined the team because my interests aligned and work aligned. So yeah, the short answer is that you can do research from a lot of different positions. The longer answer is it depends on exactly what kind of research you're trying to do and where you're trying to go. If you have a follow-up, I'm happy to try to clarify that a little bit more.
Yeah, I guess I'm just, I don't want to fall into like a data science position where I'm just trying to, really fastly apply a machine learning algorithm and not trying to figure out the best solution and not putting much thought into it. I just want to, spend time on looking for a good solution. I mean, yeah.
Yeah, that's its whole own research, or that's its whole own topic of how do you convince people to let you keep trying to find a better solution rather than putting something into a product. There's always a bit of that. I think part of that is about finding a good manager who will give you the headroom to do that. Part of it is about like just understanding how to make either incremental progress or going after the right problems and finding the right problem to tackle such that you can do that. But yeah, I think as I said, like Google Research, for instance, as an org is quite large. I don't even remember how many people we are, but there are a lot of people doing research at all sorts of different levels. Like my research, for instance, is a little less what many would call like pure research and is more applied research, but it's a place I'm happy to be, and I do think I have quite a bit of leeway or runway to explore. The project, this work we've been doing has been going on for quite a while, because people understand that some of these problems are quite hard. So as if you can convince someone that a problem is hard but solvable, then you can also get good runway. And so yeah, so again, to make all of that shorter, I think if you can convince people that the work is worth doing, like it doesn't matter so much what position you're in. If you can show that you can speak confidently and intelligently about the subject and talk about like why you think it's possible, but why you think it needs this amount of time. Like it's not necessarily about the position you happen to be in, and it's more about how well you can craft that argument, which is very true in academia too, right? That's all grant writing is, right?
Yeah.
Thank you so much.
Thank you. I guess going from being a PhD student, did you go directly into this industry position? Did you feel like the transition was good? You know, are you, I guess, if you have some new findings during your industry position, you still have time to publish them? If you want to continue publishing, do you have time to do that?
Yeah, that's a great question. That again depends a moderate amount on your team and position.
Right.
My team is perfectly happy with publishing. Like I may have mentioned no, I guess I didn't mention. Yeah, this work that I was describing, we are trying to currently publish. So hopefully it'll get published. But yeah, so if you look up other people on my team, some of them are fairly prolific publishers. They really care a lot about publishing, so they have lots of papers. That part kind of depends on a little bit more on your own motivation. So if you're in a research, for instance, I mean, I'm speaking as at Google, if you're in a research scientist position, it's somewhat more expected to publish. So that's like a clear deliverable and milestone and all of that stuff and impact. If you're in just like a software engineering position, it's a little bit more on you to do, but it still looks good, right? Like in nowhere does publishing not look good, at least.
Right. Yeah, thank you. I think Omar asked the question if PhD is required to succeed in industry.
Yeah, that's always a common but good question. Short answer is definitely no. Less than half of the people on my current team, I think, of like 25 have PhDs. The way you come into it is a little different sometimes. Like a lot of the people that are coming from not having PhDs kind of tend to show that they have more ability to like produce some of the like more software engineering kind of results that are adjacent to ML or even part of ML. And especially as ML is becoming more and more common, like it's a lot more of it is software engineering than research for a lot of these things nowadays. So to that extent, you definitely don't. It is just a lot about kind of how you'll come at it. In fact, no, that's not true. I won't even continue that line of it. But basically, yeah, it's definitely not necessary. It does help. I won't lie there that like, it is an easy way to show that you have gained experience in this. Like you'll probably, as I said, like start showing your software engineering kind of expertise as you build up kind of a portfolio of the work that you've done in industry as you go along otherwise, right? Show that I worked on these projects and had successful ML deliverables as you try to get more and more into ML positions from that route, but it's very doable.
Thank you very much. And I guess for the 25, you say 25 or 50%? 25, was it 25% that didn't have a PhD in your team?
I think it's more than half.
Our
team is a little bit different, but yeah.
Right. Like, how do they stand out to get hired if they didn't have as much of education background as some of their peers?
Yeah, that's a good question. I didn't hire them,
Right.
so I don't know, but they've done great jobs since they've been working with me. I'd say that some of them were, as I said, that's why I was trying to kind of use that as an example. Some of them did come more from like they built like pipelines or systems or productionization things for ML, and started out just by being kind of that portion of the person on their team or our team, but then slowly built out some of their kind of more background fundamental knowledge in ML too, like reading books or trying out modeling and things like that, playing around, and built up their confidence. And I mean, a lot of ML is just like trying things out and kind of getting an intuition for what works and what doesn't, such that you make fewer mistakes as you go along. And so I think, they kind of had the opportunity to do that to some extent as well, and then slowly moved more into the modeling side of the space.
Cool. Thank you so much, Matthew. Farah, do you have any follow-up questions?
No, thank you so much. I think that was very insightful, and I am sure this guideline and suggestion is very helpful for all students. It is really good to know this information, and while you have time to prepare for a career down the road.
Yeah, my pleasure. Thanks for having me.
Great, thank you. All right, if we don't have anything else, we want to thank Matthew again for your great presentation, and we'll see the rest of you on Saturday for our last workshop. Have a great evening.
Thank you so much.
Actually, we also have the tutorials for those interested tomorrow and on Friday, but otherwise we will see you on Saturday for the workshop.
Perfect. Thank you.
Perfect.
Bye-bye.
Thank you.